Okay, in this video we're going to recall all of the different things that can happen when you take the limit of a function. So first of all, we have our standard example here, x squared minus 4 over x minus 2. And the temptation is to factor the top and say, well, x squared minus 4, well, that's the same as x minus 2 times x plus 2. And we have an x minus 2 on the bottom. I'll put parentheses around it. And you'd say, well, the x minus 2's cancel. And that should equal x plus 2 by itself. But the difference between the function x squared minus 4 over x minus 2 and x plus 2 just by itself is that here if you plug in 2, what do you get? You get 0 divided by 0, right? You get 2 squared minus 4, which is 4 minus 4, which is 0, over 2 minus 2, which is 0. So you get 0 divided by 0, and of course you're not actually allowed to divide by 0. So what this ends up looking like, erase that, the graph of this function looks like the graph of x plus 2, but it has a hole above. Here I have a is equal to 2 for me. So I've drawn the graph of it here, right there. So here at a equals 2, you see there's a hole in the graph. It's not defined there at all. Okay, otherwise, it looks just like the graph of x plus 2, this linear function. All right, so the question is, does f of 2 exist? And the answer is no. You can't plug in 2 into the definition of the function. Does the limit as x approaches 2 of f exist? Remember, what that means is that as we approach, looking along the x-axis, as we approach from either side the value a, we look at what's happening to the value of the function. So for a fixed point here, we'd go up and figure out what the value of the function is, and it's equal to that value. And then for another point closer to the value a of interest, we go up again, and then we get this point, and then we pick an even closer value, and we get that value right there. And we're also doing it from the other side too. So we get this value, pick something even closer, you get this value. And so you can kind of tell that what's going to happen is they kind of want to equal this number. As we pick values closer and closer to a along the x-axis and look at the corresponding y values for the function, they're getting closer and closer to this number here, this red number, which it turns out to equal 4. It's what you would expect it to equal. And indeed, if this was the function that we were working with, and it's the graph of most of the function, when you plug in x equals 2, it wants to equal 4. So the limit means that it kind of wants to equal a certain value. So does the limit exist? Sure, the limit does exist, yes. And what is it equal to? It's equal to the number 4. So as the value of x gets closer and closer to 2, the value of f of x gets closer and closer to 2, the value f of x gets closer and closer to the number 4. Never actually equals 4 because the function isn't even defined there. So are they equal? Does f of 2 equal the limit? Well, of course not. Doesn't even make sense to ask because f of 2 does not exist. On the other hand, f of 2 might exist. Well, obviously what could happen is you could just fill in the graph. How about instead of giving you this function, I just gave you the function x plus 2 without any of this fancy stuff. Then the graph would just be the line, and I already filled in the dot for us. So in that case, f of 2 would exist, and it would equal 4. So generally speaking, the limit as x approaches a of f of x can exist, and it usually equals the value of the function at that point. You just plug in a into that function. And so, for example, that's what would happen for x plus 2. In that case, we say the function f is continuous at the point x equals a. It just means that the graph doesn't have any kind of holes in it. Okay, but the function failing to exist at a point isn't the only thing that can go wrong. It might exist, but these two things might not be equal. So here's an example of that kind of behavior. So here we have this function, and it's defined in a piecewise manner. If x is not 2, we use the same formula that we had before. And for x not equal to 2, remember, that ended up being just the same as the function x plus 2, which was the graph of a line. But this time, we give it a different definition if x is equal to 2. We define the function to equal -1 there. So I've graphed the function here. It's the same function we had before, a line with a holo in it above 2. But now, we actually have a definition for the function at x equals 2. So where that hole is, it's as if we took that point and we just moved it down over here to -1. So now, does f of 2 exist? Well, the answer is yes. F of 2 is defined to be -1. So it does exist. Does the limit exist? Well, sure. I mean, now here it's important to understand that the limit, again, is the same game that we were playing before. You pick points on the x-axis and you look at where they end up on the y-axis when you look at the point on the graph above it. And you pick points closer and closer to the value that you're interested in on the x-axis. And you do it from both sides. And you can kind of tell that, again, they want to equal 4. These points are getting closer and closer to 4 on the y-axis. So does the limit exist? Yes. And in fact, the limit as x approaches 2 of our function is equal to, it's the same limit as before. So it's 4. So notice that here the value of the function is -1, but the limit, if you kind of didn't know what was happening at the point, but you were looking at everything near the point and saying, what does it look like it's going to equal? It equals 4. So are these two things equal? No. And if they're not equal, that means that the function is discontinuous at this point. It's not continuous. So let's keep looking at some more examples. Different kinds of behavior. Alright, so here we have another piecewise defined function. When x is bigger than 2, strictly bigger than 2, it's given by the formula x minus 2 squared plus 3. So what does that look like? So you take the function x squared, and what happens when you consider instead x minus 2 squared? So this has to do with transforming functions. Subtracting on the inside means that you translate it right. So you're pushing the graph to the right by 2. And then adding 3 on the outside causes you to raise the graph up. So you're moving it up by a factor of 3. So you have the graph of x squared, which is a parabola, which looks like that. Except its apex is no longer at the origin. This apex is at the point 2, 3. And that's only for x bigger than 2. So I'm only going to draw the right half of the parabola. And since it's a strict inequality, we're not looking at x equal to 2, I put a little hole there so that you know that's not what the function actually equals at that point. On the other hand, when x is less than or equal to 2, so that's not a strict inequality anymore, it looks like the graph of x minus 3, which is just the line x, but shifted down by 3. So if you plugged in x equals 2 in particular, does f of 2 exist? Yes. It's defined by this formula, x minus 3. So f of 2 is 2 minus 3. We use this definition because 2 is equal to 2. It's less than or equal to 2. And that gives us -1. And so we have a filled in dot there. So it does exist and it equals -1. Does the limit as x approaches 2 of the function exist? Well, now that's a little bit tricky, because if we play the same game as before, you pick points and you look at their corresponding y values, it looks like it's getting closer and closer to -1 if we're coming in from the left in this direction. What happens if we're coming in from the right? Now what happens is if you pick x value, you look at where it hits the graph, and you look at the corresponding y values. To the right of x, it's actually going to look like it's converging to look like these values are getting closer and closer to the number 3. Right? That's 3 on the y-axis there. That's -1 on the y-axis here. So we have a weird behavior. As x gets closer and closer to the number 2, well, now here's the issue. It depends on whether we're coming in from the right or from the left. So we say that the one-sided limits exist. So we say the limit as x approaches 2, or a, coming from the right, so that plus sign means coming in from the right. Don't make a silly little mistake like that. It exists. So if we kind of cut off what's going on over here, and we ignore all of that, and we only look at what's happening to this side of the plane, as if I had scribbled everything. Let me actually scribble everything. It looks like the function is going to equal 3. Again, we don't care what's happening at that point, but for these one-sided limits, not only do we not care what's happening at that point, we also don't care what's happening to the left of that point. On the other hand, if you consider the limit as x approaches 2 coming in from the left, let's undo the scribbles. Now we're scribbling out this side. And again, we don't care what's happening at the value. We never care for limits, but this time we also don't care what's happening to the right. In that case, and please don't screw up between the pluses and the minus. The plus means we're coming from the right, the minus means we're coming from the left. So as we pick values to the left of 2 and we start approaching it, it looks like it's going to equal -1. So this equals -1. So what you'll notice is these two values are different, of course. They're not equal to each other. So the two one-sided limits exist, but they're not equal. And because they're not equal, we say that the limit itself does not exist. So does this limit exist? The answer is no, but the two one-sided limits do exist. So it's something. It's not as much as we would have liked, but it's something. By the way, in this case, the function is discontinuous. The limit doesn't even exist. So the function is discontinuous at the point 2, at x equals 2. So are they equal? Well, the limit itself doesn't exist, but if you wanted to say, does the value of the function equal one of the one-sided limits? Well, sure, it happens to equal the left limit. So yes, it is true that the limit as x approaches 2 coming from the left of f does happen to equal f of 2. But it's not true if I put a plus sign there coming from the right, because that would equal 3. Just clear out that scribbling. Alright, so that's one thing that can happen. Well, consider this. What if we had the same exact definition? The only difference is that now we make the bottom inequality strict and this inequality not strict. So that means that for x equals 2, we would use the top formula instead of the bottom formula. So does f of 2 exist? The answer is yes, but this time f of 2 is equal to 2 minus 2 squared plus 3. We use the top formula, which is 0 squared plus 3, which is just 3. Does the limit as x approaches 2 exist? Sure. Again, for entirely the same exact reason as before, the left-hand limit is going to of the function is going to equal -1, and the right-hand limit of the function is going to equal 3, just as before. Right? We didn't change. Again, when you're computing limits, you don't care what's happening at the point itself. So in this case, are they equal? Well, now we've changed it so that the right-hand limit happens to equal the value of the function. Again, the function is still discontinuous. The limit doesn't exist, even if the two one-sided limits exist. Alright, so now let's consider yet another example. So we have, once again, exactly the same formula, except now I've broken off the x equals 2 case all by itself, and I gave it a completely different definition. I just said that the function's value is equal to 1 there. So does f of 2 exist? Sure. Yes. And f of 2 is equal to the number 1. Just because we're using this definition. You have to, when you're looking at a piecewise function and you're evaluating a point, you look for, first you look at these conditions and you say, well, which condition do I need to use here? When I plugged in f of 2, we would use the condition that x equals 2. And that means that the function's value is 1. So again, does the limit as x approach 2 exist? The answer is, yet again, no, but the one-sided limits exist. We didn't change those at all. So as x approaches 2 from the left, and we're used to this now, is equal to -1. But if you're coming in from the right, plus sign, you're going to get 3. So are they equal? Well, no. 1 does not equal negative 1 or 3. So the limit doesn't exist because the two one-sided limits don't match up. And not only does the function not equal the limit, of course, because the limit doesn't exist, but it doesn't even equal any of the one-sided limits. So are they equal? No. Nothing's equal. So we have this weird little graph here where it's defined here, it's defined here. They have both these open dots, and the actual value there, the dot, is just sitting there by itself. Now let's take a look at what happens if we have potentially infinite limits, these kind of asymptotes. Let me switch colors to blue. Alright, consider the function 1 over x minus 2, and that's just like the graph of 1 over x, except we've shifted it to the right by 2. So we've shifted it to the right by a factor of 2. So the asymptote that used to be along the y-axis is now along the axis x equals 2. Okay, so does f of 2 exist? No. If you plug in 2, you're going to get 1 over 0. It doesn't exist. But does the limit exist? Well, as we come in from the right, we would pick values, and we would see at what the corresponding y values are. And it looks like as we get closer and closer to this value 2, you can tell, because there's a vertical asymptote here, the number gets bigger and bigger and bigger. So we would say that the limit as x approaches 2, coming in from the right of this function, is equal to infinity, positive infinity, because we go off to positive infinity. We get bigger and bigger and bigger numbers without limit. On the other hand, if you're coming in from the left, the limit as x approaches 2 coming from the left, well, what happens here is you start picking values. You look at the corresponding values on the y-axis, and now they're not getting bigger, they're getting smaller and smaller and smaller. They're not running off to infinity, they're running off to a negative infinity. So we get a negative infinity here. So, typically when you actually have a formula and they ask you, what's the limit as x approaches 2 of 1 over x minus 2, your inclination is to first just kind of plug in the value. You plug in 2. What you get is 1 over 0. And you might be tempted to say, so the denominator is shrinking, which means the overall thing is getting really big. So it's infinity. But as this picture shows, that kind of reasoning doesn't quite work. It might be infinity, but it might also be negative infinity. And here, it's infinity coming from the right, but it's negative infinity coming from the left. So the two one-sided limits exist, but of course infinity is not the same as negative infinity, so they're not equal. And because they're not equal, those two one-sided limits exist but are not equal, the limit itself does not exist. So are the equal? Does the value of the function exist? No, it doesn't even exist. There's nothing to compare. On the other hand, you might have asymptotes that work out just a little bit better. Consider this function 1 over x minus 2 squared. So this looks more like the function 1 over x squared, whose graph looks something like this. It looks basically just like 1 over x, except it's a little steeper, and and they both point up. They also have asymptotes, by the way, going off to 0 here. Alright, so does f of 2 exist? No, there's an asymptote there again. Does the limit exist? Well, now this time you'll notice that coming in from the right or coming in from the left, picking values coming in either way, they're both shooting up to positive infinity. So this time the answer is yes. And the limit as x approaches 2 of this function is equal to positive infinity. Are they equal? When I say they, I mean f of 2 and the limit, and it doesn't even make sense because the value f of 2 doesn't even exist. But in this case, the limit did exist, and it was infinity. Again, if you plugged in a 2 directly into the formula, you'd end up with 1 over 0. So here you got a 1 over 0, and it turned out to be positive infinity. But remember, you can't just always say that, because you could have a situation like this, where it goes to negative infinity, or it comes to positive infinity in one direction, negative infinity in the other. And then finally, just to be done with it, if we put a minus sign in front of the previous formula with that x minus 2 squared, the graph is going to look like this. And as we approach a coming in from either left or right, they're both going to go to negative infinity. So does f of 2 exist? No. Does the limit exist? Yes. And it equals coming in from either direction, the one-sided limits exist, and they're both equal negative infinity. So that's possible. And this question doesn't even make sense because f of 2 doesn't exist. So here we go. In each of these cases, again, if you plug in, you'd get negative 1 over 0 into this formula. So division by 0 could be infinity. It could mean negative infinity. Or it could be, non-defined because the two one-sided limits don't match up. And I'm assuming that the numerator isn't 0. In each of these cases, it wasn't 0. In a case where the numerator is 0, that would be like the very first example we considered, x squared minus 4 over x minus 2. You plugged in a 2 there, you got 0 over 0. Usually whenever you get 0 over 0, you have no idea what's going on, and you have to do some algebraic simplification or something, some manipulation to help you figure it out. Alright, so in each of these cases, I mean, if you look at all these examples and consider them, we've seen interesting things. We've seen cases where the function exists but the limit does not. The limit exists but the function does not. They both exist but they're not equal. One-sided limits exist here or there and the function may or may not equal them. So we've got lots of examples. You can go back and watch the video and see all of the different, rich variety of things that can happen. But in each of these cases, when the limit failed to exist, it's because the one-sided limits both existed, but they weren't equal to each other. So you might think, okay, so the one-sided limits are always going to exist, but whether or not they're equal to each other will determine whether the overall limit exists. But that's not the only thing that can go wrong that can prevent a limit from existing. So even the one-sided limits may fail to exist in the first place. So here are some great examples. There's the function f of x equals sine of 1 over x. And what this looks like is it kind of looks like a sine that gets infinitely scrunched up as you get closer and closer and closer to the y-axis here. So it never actually equals anything at x equals 0. Obviously you can't divide by 0. This function isn't defined. So f of 0 does not exist. But what about the limit? Well, now that's where things start to get a little bit awkward and complicated. As you pick values closer and closer to 0, coming in from either the right or the left, it doesn't matter, it just kind of oscillates infinitely. So depending on which values you pick, you can kind of always arrange. Let me pick a different color here for a moment, green. Okay, so for example, if I happen to magically, just by luck of the draw, always pick the zeros as I get closer and closer, the place where this curve hits the x-axis, then I'm going to think, so the y values are always 0, so it's going to go to 0. Okay, but if I happen to, by luck of the draw, pick these peaks each time, it would look like it's going to 1. Or if I could pick the lower peaks, and then it might look like it was going to negative 1. Or if I make my choice judiciously, I can take any value I want. I can make it look like any number between negative 1 and 1. I can make it look like a half. I can make it seem like it's going to always look like a negative 1/2. Or if I don't get lucky, if I don't pick my choices of points on the x-axis judiciously at all, then it's probably going to end up with some ridiculous set of values that just hop forever between negative 1 and 1. So here, there's no regular behavior. I can't finish the phrase as x gets closer and closer to, approaches, here it's 0, not 2, approaches 0, f of x approaches, look, it's not going to infinity or negative infinity, and there's no number that I can put here that would make this a true statement. As x gets closer and closer to 0, this thing, f of x, oscillates between all the values between negative 1 and 1 infinitely often. So here, the one-sided limits don't even exist. This happens coming in from the left and from the right. On the other hand, an interesting function to consider is x squared sine of 1 over x. Just so you don't think that these kind of infinite oscillations always leave you high and dry without a limit, x squared of sine of 1 over x, the graph of it looks more like this. Okay? Now, it still oscillates, but it kind of oscillates between these two parabolas, which means it's shrinking in towards the origin as you approach the origin. So as you pick values of x, and you look at their corresponding values of y, in spite of which things you choose, you're always going to get closer and closer to 0. So in this case, Obviously, you can't plug in x equals 0, so it's not defined there, but the limit as x approaches 0 of x squared sine of 1 over x is equal to 0, coming in from the left or from the right. Your y values are always going to shrink down to 0. They'll actually, if you pick this point, it'll shrink from both sides. So infinite oscillation doesn't always mean that the limit fails to exist, because it can still narrow in. But these are just some nice examples to have in mind.